Hello everybody. You are watching this video because I'm out of town today. This is a video about section 2.6 about graph transformations. It builds directly on the graphing things we've been doing throughout chapter 2. These are ways to think about graphs of functions that you get from older, more familiar functions. So to motivate this material, here are two familiar functions, x squared and x cubed. We have sketched the graphs of both of these on the board. These are famous functions. You are just supposed to know what their graphs look like. Okay, these are supposed to be familiar. Here are some functions that are perhaps less familiar, not x squared, but 4 minus x squared, and not x cubed, but quantity 5x cubed, and then plus 4. So what we have here are two functions down here that in their formulas, in their equations, are similar to these guys up here. Not the same, of course. But you know, you basically have an x squared versus an x squared. This x squared is negative, and there's a plus 4 here. Not an x cubed now, but a 5x quantity cubed, and then again with a tack on of a plus 4. So the point of this section is, if you understand what that looks like, or you understand what that looks like, then you understand what things like these look like, or what that looks like. Okay, if you know what x squared looks like, you should be able to tell me what 4 minus x squared looks like. 4 minus x squared is similar enough to x squared that you should be able to picture that as well. So in a calculus course, which is where most of you are moving on to, and in particular my calculus course, I expect my students to know what these look like. Okay, I also expect them to know what these look like without too much effort, you know. Like on an exam, they are just expected to know what that looks like, right? I don't explain it to them or anything, right? It comes up in the context of a bigger calculus problem. They're supposed to know what it looks like. So the point of this video today is just, okay, I know what these look like. How could I figure out what these look like? What do their graphs look like in terms of the original graph? So just to emphasize that point, let me graph a couple of these for you. There's y equals x squared. 4 minus x squared looks like this. Has the same basic shape, right? It's still sort of a U shape, a parabola shape, but you know, sort of going the other direction, opens down, and the vertex has been moved up to 4, right? It used to be that this thing bottomed out at y equals 0, now it tops out at y equals 4, but same basic shape. And again, on a calculus exam, I would just expect students to know that's what 4 minus x squared looks like. Here's y equals x cubed. If I graph instead 5x quantity cubed plus 1, here's what that looks like. So going from the black curve to the red curve, it looks like it's been squashed quite a bit, right? And it's also been moved up. So I squashed and moved up. So the question is, how could you have anticipated those changes based on these formulas? Okay. So let's begin by talking about how you move a graph up or down. If you remember anything about graphing transformations from a previous course, you most likely remember this. If you want to take a graph that's familiar to you and move it up, you simply take the formula of the old function and add a number to it. And the number you add determines how much you move up. If you want to move down, you just subtract the number off. So let me go back here to my picture. Here's y equals x squared. So I could do y equals x squared plus 1. See, all it did was it took the original graph and moved it up 1. So there's the two graphs together. Or I could do y equals x squared minus 1. Oops, that's minus 11. Minus 1. Right? Same exact shape. All that has happened is that you have literally picked up the original and moved it down 1. So same thing with 2, right? Same thing with 2.5, whatever. You just keep moving it up or down. That's how a vertical transformation works. You take the original formula, which was x squared, and subtract or add a number at the end of that. Okay, so this is how you move something up or down. You can also move things left or right if you want to. That's a horizontal shift. So how do you take this little blue curve here and move it to the right or move it to the left? You know, this is actually slightly more complicated. What this is saying is, if you want to move something to the right by c units, what you have to do is go inside the function f and replace all the x's you see with x minus c. So remember, f of anything, Doesn't matter what's in here, smiley face, x minus c, whatever. This means take what's in here and replace all the x's with whatever is in there. So let me go back to this graph here. There's y equals x squared. Okay. Suppose I come along and I say, oh, I'm going to replace all the x's I see, and there's only one of them, right? I'm going to replace all the x's I see with an x minus 1. So where there used to be an x, there's now an x minus 1. Notice the effect, right? It moved it to the right by 1 unit. I can move it to the right by 2 units if I want to, by 3 units if I want to. Okay. So that's how you can shift something to the right. Now, what students typically forget here, because this is actually the opposite of what you would expect that doing x minus 1 would move things to the left, wouldn't you? Because you're subtracting, right? Now, unfortunately, with horizontal shifts, things work the opposite of the way you expect. Doing an x minus 1 instead of an x moves you to the right. Doing an x plus 1 moves you to the left. So replacing x's with x plus 3's will move to the left by 3. So if I combine these two things together, we'll do like this. Here's x minus 1 squared minus 1. What is that doing? Well, replacing an x with an x minus 1 moves me to the right by 1, and then subtracting 1 off the end of that should move me down by 1. And that's what's happened, right? Over 1, down 1. So you can use these two transformations in tandem to move left, right, up, or down at the same time. Okay. So let's just pause and do a question here. Write down a formula for a function g whose graph is basically the graph of x squared, right? But what I want you to do to x squared is shift it up 4 and right 2. Okay. So here's what that looks like. If you want to shift something to the right by 2, you have to replace every x you see with an x minus 2. And then if you want to shift the resulting thing up, you add a plus 4 at the end. So x minus 2 quantity squared plus 4 moves me right 2, up 4. And just to emphasize this more, this function x squared only has one x in it. Let me just put another x in it. So there is, here is x squared plus 2x, okay? Suppose I want to move that, what is it? Up 4 and right 2. If I want to take this guy and move him up 4, right 2, then what I have to do first to move it to the right is take every x that I see and replace it, every x that I see and replace it with an x minus 2. Okay, so in this example here, there was just a single x. So I took that single x and replaced it with an x minus 2. If there are more x's, you have to do that more. You have to take it and shift it to the right by 2. So x squared plus 2x, that original graph is still here. I have picked it up and moved it to the right by 2. And then if I want to move that up 4, I can just add it up 4, right? So over 2, up 4. So you can move things to the left or the right. You can move things up or down. You can also do things called reflections. So you use the x-axis or the y-axis as a mirror. So here, to reflect this blue curve, you reflect it across the axis like a mirror, the x-axis. So the result, if you were entirely above the x-axis, the result of a reflection will be entirely below. You can also reflect across the y-axis if you want to. Use the y-axis as a mirror. So if your blue curve is entirely to the right of the y-axis, the result will be to the left. So the way you take a graph and reflect it across the x is you multiply the entire function by -1. That's what this is saying. So if you take f of x and hit it with a -1, you will reflect across the x-axis. Okay, so right here is x squared plus 2x. It looks like that, right? And actually, let me just go ahead and move it up. Okay, so there's x squared plus 2x plus 1. If I want to reflect that across the x-axis, what I have to do is hit everything in sight with a negative sign. So negative x squared minus 2x minus 1. That's the original function negatived. And notice what happens. the new function is mirrored across the x-axis. If I go back to the original function, x squared plus 2x, let me zoom out a little bit here. There's x squared plus 2x. If I want to reflect that, I can as well. I just slap negatives everywhere, and that's what happens. So the original black curve is like this, right? I used the x-axis as a mirror. So this piece of the curve here got reflected across down to this piece. This piece that went below the x-axis got reflected above. And then this piece over here that was above got reflected below. So every single piece treats the x-axis as a mirror. Okay, so that's how you can reflect something across the x-axis. If you want to reflect across the y-axis, you can do that as well. What the slide is saying is, don't multiply everything in sight by a negative. Right, that's what this is saying. Here's f, negative it. To reflect across the y-axis, you replace every x in the formula with a negative x. So it's just like this f of negative x guy here. It's just like back with horizontal shifts. These are saying replace x with x minus c. Replace x with x plus c. This is saying every x you see replace with negative x. So let's come back here to the picture. This is x squared plus 2x. What would it mean to replace every x with a negative x? Well, let me just literally type that. Instead of an x, I have a negative x, quantity squared. Instead of plus 2x, I have plus 2 minus x. Okay, so what happened? Whoa. The y-axis here acted as a mirror. This little piece here on x squared plus 2x got mirrored across the y-axis to that. And this piece here on x squared plus 2x got mirrored across to that. So in case that isn't clear enough, let me just go ahead and take x squared plus 2x and move it to the right a little, or sorry, move it to the left a little bit. So let's do x plus 3 squared plus 2, x plus 3. Okay, so it's way over there, right? Now let me take this guy and move him across the y-axis like a mirror. So again, to take this guy and reflect him across the y just means every x I see replaced with a negative x. So let me just do that. And there he is, right? The y-axis here took this guy over here and mirrored him across. So there's his reflection across the mirror of the y-axis. So the upshot of all this, right, is you can use either axis as a mirror if you want to. So let me return to one of those opening functions, 4 minus x squared. How could you have predicted what that looks like? Well, you can think of 4 minus x squared as negative x squared plus 4, right? It's the same thing. So what does negative x squared by itself look like? Well, negative x squared, what have you done? You have taken x squared and hit it with a negative. So that reflects things across the x-axis. That's what this previous slide says. If you hit everything in sight with a negative, it reflects across the x. So forget about the plus 4 for a second. If somebody says, hey, think about negative x squared, they're asking you to reflect x squared across the x-axis. So back here, let me just do y equals x squared. There he is. And then y equals negative x squared, we've already looked at, but it's reflected. Okay, oh, but it's not just negative x squared. We also, once we slap a negative there, that plus 4 means add 4, means move up. So it's sort of a two-step process here, right? You reflected, and then when you were done reflecting, you added 4 to shift the whole thing up. So let me now just do that. Negative x squared plus 4. And there you go. There's the shape that I started with at the beginning. So again, this is something that a calculus student should be able to do in about like 5 seconds of thinking, right? This, if you've done this enough times, this function should be clear to you that it's a transformation of x squared, and that transformation consisted of two pieces, a reflection and an upward shift. Okay, so here's sort of another question that gets at if you understand transformations or not, sort of a backwards question. It says, hey, write down a formula for g whose graph is obtained from this x squared plus 2x guy that we've been dealing with. What I want to do is I want to shift this guy down by 3, then reflect across the x-axis, then shift left 4. So this is 3 steps, and we have to do them in order. So first, let me shift down by 3. That requires a -3 there. Then for the next step, we have to hit everything with a negative sign. So the -3 becomes +3. The x squared becomes -x squared. 2x becomes -2x. And then at the end, to shift left by 4, we have to replace all of our x's with x plus 4, not, as you might expect, x minus 4. So here's the end result of those 3 steps. So first down, then reflect, then left. And by the way, order matters here, right? If you jumble up the steps, you'll get a different function. So make sure if you see a question like this, you follow the exact order of the language. Okay, you can also stretch and shrink things if you want to. So just to motivate what this is saying, let me graph the sine function. Now, if you're rusty on trig, or you've actually never even seen trig, you might not know what this is. Okay, so don't worry about that. I just want to graph something that has a wave. So we will deal with these functions later. For now, just take this wave as a given. Suppose I take that wave, though, and what I do is I multiply by 2. So I used to have just sine x, now I have twice sine x. You see the result there? What happened was a vertical stretch. I sort of took the graph and pulled on it in a vertical direction. And if I do like 3 sine x, it becomes more exaggerated, right? The bigger that coefficient is, the more I'm pulling on the function. I could also do not 2, but maybe a half sine x. See what that does? That squashes, right? It's not a vertical stretch, it's a vertical shrink or a vertical squash, whatever word you want to use. A third, a sixth, right? The smaller I make that number, the more I'm squashing it down. So that's all this slide is saying, is that if you take a function and you smack it with a number, right? You multiply everything in sight by c, a number c. If that c is bigger than 1, you're getting a vertical stretch. If that c is between 0 and 1, so it's a fraction, you're doing a vertical squash, a vertical compression. Okay, the last thing, I think I have 2 more things. Yep, okay. So the second to last thing I want to mention to you is that if you can stretch vertically or squash vertically, you can do the same thing horizontally. So just to motivate what that slide is saying, let me clear this out. Okay, so again, my original graph is this wave here. Suppose that I take that wave and I don't put the 2 out here. I don't multiply things by 2. What I do instead is, everywhere I see an x, I write instead a 2x. Okay, so there used to be an x, now there's a 2x. It's a replacement thing. You notice what happens? It got squashed inward. So it's kind of hard to see, so let me turn this off. So there's the wave just going along at whatever rate it was rising and falling, Now I've taken it and I haven't vertically pulled it at all. This graph still bounces up and down between the same values, but I've squashed it inwards. So I've sort of just taken my hands on left and right and just pushed inwards. I compressed it. And if instead of a 2 I do a 1/2, notice what happens? I sort of pull it. I stretch it horizontally. I pull the waves out. Let's just zoom out a little bit. So it's the same kind of wave, but it's much longer. It's been drawn out. So that's what this slide is saying. If you take every x that you see and you replace those x's with, like, say, 2 times an x or 3 times an x, whatever, you're actually going to shrink the graph horizontally. Again, this is the opposite of what you might expect. If I take every x I see and replace with a 2x, well, 2 is kind of big, right? So you might expect things to get stretched out, but they actually don't. They get compressed. They get shrunk. So that's what this first thing is saying. If you want to shrink things by a factor of a half, make things happen twice as often, you would you would replace x with a 2x. If, on the other hand, you want to stretch things out, you replace every x you see with not 2x, but say a half x or something. So again, here there used to be an x, I'll do a half x. And now things get pulled, they get stretched horizontally. So that's how you can stretch or crush things horizontally. Again, just like with horizontal back and forth, left or right, you are replacing x's with something. You aren't replacing with x minus 5, because you're not doing a literal move left or right. You're replacing an x with like a 5x or a fifth x or something. Okay, let me close this video by giving you just a bit of vocabulary that we will need later. A function is even if f of negative x equals f of x. What does that mean? Well, remember, what does f of negative x look like? That should remind you of, way back here, that. Okay? If you take an x and replace it with a negative x, you are using the y-axis as a mirror. You're reflecting across the y. So way back here with the definition of even, what I'm saying graphically is that an even function is a function so that if I reflect things across the y-axis, I haven't changed anything. I get the original function back. So, just to show you what that looks like, get rid of this. Here's x squared again, right? Suppose I try to reflect this across the y-axis. The way I do that is I would take my x and replace it with a negative x. Okay, so I'm going to hit enter here and let's see what the graph does. The graph is the same. Okay, again, there's x squared. If I replace x with a negative x, I haven't changed things. So that's what it means to be even. If I try to use the y-axis as a mirror and nothing changes, the function is even. So by the same token, right, x squared plus 2. That's an even function because, again, if I replace x with a negative x, I don't change the graph at all. It's the same. So these functions, these even functions, they are symmetric with respect to the y-axis. If you try to use the y-axis as a mirror, you don't change anything. By contrast, though, here's x cubed. Now, if you try to reflect across the y-axis, let's do it like this. If I replace my x with a negative x, notice what happens. You get a different picture, don't you? You get a different function. So x cubed is not even, because when I reflect it across the y, I get something different. Okay. So lastly, a function is odd if I reflect across the y-axis, I get the same thing as if I reflected across the x-axis. Okay? Because remember, slapping a negative on a function reflects across the x. So this is saying, look, if you reflect across y, you reflect across x. If those things are the same, you get what's called an get what's called an odd function. Okay, so what might that look like? So let me go back to x cubed. Okay, there's x cubed. Suppose I wanted to reflect x cubed across the y-axis. What I would do is I would say, okay, replace my x with a negative x. Okay, so this is what happens when you reflect x cubed across the y. Okay, well, what if I were to reflect x cubed across the x? Reflecting x cubed across the x means just slap a negative in front of the function, right? Don't replace x with something, just literally put a negative sign there. Okay, so again, you might have missed that. I hit enter. It's giving me the same graph I had a second ago. Here is x cubed reflected across the y, quantity negative x cubed. If I try to also graph just negative x cubed, it's the same thing. Okay, so that's what it means to be odd. If you replace every x in sight with a negative sign, and that's the same thing as just slapping a negative sign on the function, it's called odd. So just to give you one more example, again, if you don't know what sine is, that's fine. Okay, we'll get to it later. But with sine, that's what the graph looks like. Okay, so suppose I reflect across the y-axis. Well, that would mean replacing x's with negative x's, right? Okay, so let me turn the original graph off now. Here is sine x reflected across the y. Well, if I want to reflect sine across the x, what I then have to do is not replace x's with negative x's, but just slap a negative sign on. So I'm going to hit enter here, and notice what happens. Nothing new, right? It just went right on top of the sine negative x graph. So sine is also odd, because if you reflect across the y, you get the exact same result as if you reflect across the x. Now, not all functions are odd, right? So here's an example of something that's not odd. Y equals x squared. If you reflect x squared across the x-axis, you get, that guy, right? Negative x squared. That's its reflection across the x. If you reflect it across the y, you just get itself. So x squared is even, not odd. Okay, so you can be even, you can be odd, and generally you can't be both. Furthermore, there are some functions that are neither of these things. So let me just do like, let's think about x to the third plus 1 maybe. Okay, so there's that function. If I reflect that guy across the y, I just have to put negative signs everywhere. So negative x cubed minus 1. Oops, I'm sorry. If I want to reflect across the x, I misspoke. If I want to reflect across the x, I just put negative signs everywhere, right? Now, if I want to reflect across the y, I replace all of my x's with negative x's. So here's the result when I reflect across the y-axis. So you can see these are different functions, right? They didn't give you the same picture. So x cubed is neither even nor odd. X cubed plus 1 is neither even nor odd. Okay, so functions aren't like numbers. Like with whole numbers, every whole number is either even or odd. Functions don't have to be either even or odd. So the language here is slightly confusing because of that. But just keep in mind the geometry here. So with the geometry, you're even if reflecting you across the y-axis doesn't change you. You're odd if reflecting you across the y-axis gives the same result as reflecting across the x-axis. Okay, so in sum here, we're done. You should be comfortable with all of the transformations: vertical, stretching, and shrinking; horizontal, stretching, and shrinking; reflections, horizontal, left and right; vertical, up or down. You should be comfortable with these, and you should be able to put them together in questions like this, basically, or like this. You should be able to do this. Given a function that you basically know what it looks like, you should be able to tell me what a new function looks like. You should be able to tell me exactly what this function looks like in terms of the original one. You should recognize the transformations that happened here. Okay, so if any of this confuses you, or if you have any trouble with the in-class problems or with the homework problems, please email me or see me on Monday. Have a good weekend.